Oh, hi there, and thanks so much for showing up for your math learning today, everybody. I am, as always, your humble math servant, Mr. Jennings, struggling with the Zoom once again. Here we go. We have been asked to graph y equals x squared minus 2. So, it has been suggested to us that we use a table of values. People feel like that's like the best strategy here? Anyone have a different strategy? Let's go. Let's use a table of values to graph this one. We're going to pause the video. Zoom. Okay, so let's take a look here. This is what my table looks like. So if I put that on, I've got minus 3. So minus 3 over here, and then 7. 1, 2, 3, 4, 5, 6, 7. That's right there. Minus 2, 2. That's this point. 1, minus 1, minus 1. Oh, that's interesting. 0, minus 2. There's our y-intercept. 1, minus 1. Oh, there's also our vertex. And then it's symmetrical around that axis of symmetry, which is the y-axis in this case. So there's our parabola. It's going to look something like this. If I can hit points. It is, again, a beautiful curve traveling through. Isn't that neat? Okay, so what do you notice? Well, the vertex, it's at 0 in the x, minus 2 in the y. It's opening upwards, and its step pattern, leaving the vertex. I'll just draw a step pattern in red here. We're going to go up 1, up 3, and up 5. Oh, it was just like Friday when we looked at like y equals ax squared. This one is just like doesn't have an a. Its step pattern was also 1, 3, 5. So the step pattern hasn't changed because here the a value is 1. So it's the same. It's just an x squared type parabola. And if I graphed y equals x squared, which if you're not dreaming about this and seeing it in your dreams yet, let's lock in. Okay, maybe I don't dream about this. But here we go. This is what a equals x squared looks like. It's just the squares, right? So we go 1, 4, 9. 0, 1, 4, 9 there. This is what our normal ax squared looks like in the positive direction. And then in the negative direction, minus 1 squares to 1. Oh, here's a way that you can remember it. Minus 1 squares to 1, minus 2 squares to 4, minus 3 squares to 9. What's up? How can I help? Yeah. So, here is the cool thing if we're looking for patterns. What did this minus 2 do to this parent function to create this other function, y equals x squared minus 2? What was the function of that minus 2? What was its effect? How did the red parabola change and become the blue parabola when we said minus 2? It went 2 in what direction? Yeah, it went 2 down. So we can use our visual understanding here. Every point on that y equals x squared just went down by 2. Because this minus 2 just subtracts from the value of the function. It will be the last thing that the bedmus bouncer lets in, and he's going to pull every final value down by 2. It's just like that. So we can visualize that this way. Down by 2, 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 down by 2. This is what we would call a translation. The whole shape has been translated down 2. That's it. So, what do you think is going to happen here with minus 2x squared plus 8? Well, let's quickly do our table of values. G at minus 3 is going to be minus 2 times minus 3 squared plus 8. And if any of you are still wondering about these brackets, I have put x in brackets there. And if I punch it exactly like that in my calculator, I'm gonna like what happens. I'm gonna like the next thing. Sorry. Okay, so I get minus 18 there. Sorry, that's skipping steps. I get minus 2 times 9 plus 8. Oh my goodness, that's so frustrating. That's minus 18 plus 8. That is the same thing as minus 10. So g at minus 3 is way down there. It's off our graph. Oh dear. So here's the cool thing that I like to do. I think it's cool. I don't know about you kids, but I think this is cool. I just go in here and on my whiteboard or whatever, change these values. I'm now interested in minus 2. That was minus 10. So I put in minus 2 here. Minus 2 squares to 4. Minus 2 times 4 is 8, but negative. Negative 8 plus 8 is, there's a 0. Oh, we found a root. It's got a root and it's right there. Okay. Minus 1. Let's just go ahead and use my little trick. Okay. So we put in minus 1 here. Minus 1 squared is 1. Minus 2 times 1 is minus 2. That's 6. So that's minus 1, 6. 1, 2, 3, 4, 5, 6. There. Now let's try 0. Any predictions on where 0 is going to be? This one. 8. Good. I like it. Let's just confirm. 0 squared is 0. Negative 2 times 0 is 0. 0 plus 8 is indeed 8. Cool. Now let's try 1. See how fast? I'm not doing anything like super amazing. I just do the work really fast. Because I just do it. Okay. Minus 2 times 1 happens to be minus 2. Minus 2 plus 8 is, 6. Oh, I visually see that we've found the vertex because we have symmetrical points there. And so this is the axis of symmetry, meaning I could take this point and reflect it over there. So visually, that point 2, 0 is going to be on the parabola because minus 2, 0 is on the parabola. And we're symmetrical around the line x equals 0. This one. Because it goes up there and then comes back down. It's like saying, where's the vertex? Here. Where it touched the roof, yeah. Okay. 8, 6, 0, minus 10. Okay, symmetrical. Symmetrical around here. So, we now have it graphed. And that's what it looks like. So our vertex here, 0, minus 8, its direction of opening is now down. It's opening down, and we can see why. Why is this opening down, this g of x? Because a value is negative. I love it. Okay, this is minus 2 here. And then, here's what we were doing on Friday. We were doing minus 2 times the typical step pattern of one of these parabolas, which is 1, 3, 5. If you multiply that in to see what the new step pattern should be, it should be minus 2, minus 6, minus 10, which is just like the example we looked at this morning, right? Still this morning. And then check it out. Here is our step pattern. There's minus 2 going away from the vertex, minus 6, and then minus 10 down there, like that. So it matches that, Connor? Positive 8? Oh, I wrote down negative 8. Chase, do you want to record an error for me? I wish I could tell you I did that on purpose so that you could have this shining moment, but that was just me dropping the ball there. Okay, all right. So can you sketch like minus x squared plus 4 on the graph without making a table of values? Sure I can. Watch me go. I will do that right now. And you can be amazed at how easy this is. So I'll talk through it so that all of the thinking that happens in my brain you can see on the page. I know that it's going to have a c value or a y-intercept at 4. I also happen to know that that's the vertex. And we're opening down because we have minus x squared. So I'm just going to use my step pattern around that 4 and kind of do this. So I'm going to go over 1, down 1, over 1, down 3, and over 1, down 5. And that's there. Over 1, down 1, over 1, down 3, over 1, down 5. So this is x squared, sorry, negative x squared plus 4. All right. That's what that would look like. Let's verify in Desmos. I got Desmos open. It's fast to do this. Let's first take a look at, we were looking at g of x equals negative 2, oh, you got to type in it. This is g of x. G of x is equal to negative 2x squared plus 8. That was that one. And then we were asked about negative x squared plus 4. Looks like that, just like I showed you. Shares those two roots, just like it did on my diagram, going from step pattern. And it looks like that. Okay. So this point here, 4, that gives us this point 0, 4. That's that vertex there. This one here is at 8, 0, 8, up there. There's where those land. Okay, cool. Let's keep going. All right. So in general, here's the general thing we can see about these parabolas. Y equals ax squared plus k. Where do they have their vertex? Their vertexes were there, 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 and there. They're all along what line? Huh? Their vertexes are their y-intercepts. Their vertexes are on the y-axis. None of these have a bx term. None of them have any slope at the y-axis. They're flat there, and then they come down. So these graphs are all parabolas that have a vertex on the line x equals 0 or the y-axis. That's all true. That's all true there. Okay, so let's take a look at this one. I bet this one doesn't have a vertex on the y-axis. What's that? Oh, I thought you were, because I knew you were on this one. So there's a funky thing that's happening here, Christian, yeah? Yeah. So here, f at minus 4 equals minus 4 plus 2. Put it in brackets, squared. Minus 4, 4. Let's try minus 3. I don't know why there's 2 minus 2's there. You notice that? What would be more useful to test here? Yeah, let's change that together. So just because I put it in front of you doesn't mean it's perfect. Okay. Sam, thank you for helping me find that so that I could prepare this just little teachable moment. Okay, so we had 3 minus 1. Oh, look at this. If we put in minus 2 here, watch what happens in here. Okay? Okay, if I just remove these and I put in here minus 2 for x, I'm just substituting in minus 2 there. Minus 2 plus 2 is 0. 0 squared is 0. It's there, boop. 0. Now let's try minus 1. See what happens. Substitute in minus 1. Minus 1 plus 2 is indeed 1. 1 squared is 1. Oh, look at that. It turned around and went back up. And if we put in 0, something also interesting will happen. So if we substitute in 0 for x, we get 0 plus 2. 0 plus 2 is 2 every day of the week. 2 squared is 4. So there it is there. Still symmetrical. Symmetrical with that point. So we're not having a lot of surprises there. If we put in 1, we're going to find that 1 plus 2 is 3, and 3 squared is 9. So we are up there at 9. And then if we put in 2, we would have 2 plus 2 is 4. 4 squared is 16. So we're off the graph somewhere up here. Like that. Okay. So then our parabola looks like this. Something like this. Thanks. I'm getting better. I was just feeling that myself. So that you noticed at the same time. It's satisfying. Okay, so anyway, what to say about this? One other thing I wanted to highlight here. Suppose you want to find the y-intercept of a function, and it's like this. We can't directly see it. When you substitute x equals 0 into the function, you are finding the y-intercept. So that's one technique for finding the y-intercept of a function. Just feed it the value 0, and you will find the y-intercept, by definition, because the y-axis is the line x equals 0. Okay, so there it is. Where is the vertex in this case? Where's the vertex, somebody? The vertex is at negative 2, 0. Lovely. There it is right there. Negative 2 in the x, 0 in the y. Oh, look at that. This plus 2, if you flip the sign, you get the x value of the vertex. And then this k value that's not there, this plus k, that is there. It's plus 0. So we don't write it. I happen to be 45 plus 0 years old, which is a weird way of telling you my age. Oh, and then we see the direction of opening is still up, and the step pattern is 1, 3, 5, dot, 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 dot. So the a value here is still 1. So the step pattern is unchanged, 1, 3, 5. Okay, our step pattern is still 1, 3, 5. But over here, what will our new step pattern be? Good. With this one, Chase is looking at this a value here. A is minus 2. And he says, well, I know that if I take minus 2 and multiply it by the typical step pattern, I get the new stretched step pattern. So that would give me minus 2, minus 6, minus 10. Lovely. And then, where is this one going to have its vertex? 1, 0. Love it. How did you know that? Awesome. That's great. So there it is. Here is the vertex at 1, 0. Because look at that. When x is 1, that whole thing in there is 0. Right? We've already seen that if x is the opposite sign to that number, that's where you get that situation. So the y value, or the value of the function, is just the value of k, which in this case is plus 0. So there it is. So it's there, and it has this step pattern, over 1, down 2, back 1, down 2, and it goes off the graph. And really, there should be a different piece of graph paper there so you could see more of this thing. We should move that up. Sad. So sad. There we go. So this. What? Why isn't it going up? Different question? Oh, cool. So let's see if we can together. I'm getting bored of making tables of values just like you. So I want to use the shortcuts too. I skipped making the table of values. But you could verify that with the table of values and we'd be right. Now, let's do this question. F of x is equal to 2 times x plus 3 squared. What will that one look like? Where's its vertex? Is this number or this number giving us information about its vertex? The second one. So where do we find the vertex here? If that's a plus 3. That's correct. So we would have a vertex here. Let's do this one in red. Minus 3, 0. There's this one's vertex. This number is the A. A is equal to 2 in this case. That changes our step pattern. Chase is already able to tell us that its step pattern would be 2, 6, 10 when we do this. 2, 6, and 10. So if we go over 1, we should go up 2. Over 1, we should go up 6. 1, 2, 3, 4, 5, 6. And then back 1 up 2, back 1 up 6. That's that parabola there. And then you could verify with a table of values to make sure you're getting 100% on things like tests. So, in general, when we have these parabolas, y is equal to ax minus h squared, look at that. Look where their vertexes are. Look where their vertexes were on the x-axis. Because the value of k there is 0. So now we put these things together, okay? We have looked at vertical stretches and compressions. These are the A value. Changes the curve. It changes the shape, like inflating it, making it taller, or squishing it, making it more flat, okay? The A value stretches and reflects. So these are negative A values. If A is negative, boop, it will reflect in the x-axis. So we've seen a number of those examples today. You want to always be sort of linking those things to your bigger patterns that you're noticing in this course. We can also shift up or down by adding to the function. Adding to the outputs. And that would be adding here with the k value. We saw that k value moves things up or down. And that just adds on. The Bedmus bouncer keeps him out there last to incorporate him, shift the whole value of the function either up or down. Okay? If you want to move that function left or right, it has to be in there with the x value. Okay? So if you want to shift right or left, that's the job of h. If we add or subtract to the inputs of the function, you are shifting it left and right. And it's really that simple, and this is what I'm talking about the emperor wearing no clothes. It's like we're only doing 4 things. We can stretch it big by multiplying it. Not really a surprise, right? You multiply 0, it stays the same. You multiply 1 by something, it gets a little bigger. Multiply 4 by something, it gets 4 times bigger than 1 got bigger. It stretches with multiply. If you multiply by a negative, it just flips. Again, not particularly surprising. The positive numbers were up there, they become the negative numbers. If you want things to lift up, just add on to them. If you want things to all go down and stay the same shape, subtract from them. And if you want to shift it left or right, you just add on or subtract from the inputs. Yeah. So that's basically the whole thing. So, try this example. I'll come around and see how people are doing. And then we'll have some time for catch up with textbook stuff tomorrow and Wednesday.